Hello, I am Stefan Popp, and I found out that searching ants combine systematic meandering with correlated random walks at different spatial scales. First, imagine you were searching for coins in a wide field like this one, where you would have to return to your starting position after each find. What strategy would you follow? And this is exactly the question I'm trying to answer in ants. Just how random are these movements that you can see here? Well, the animal movement literature usually assumes some kind of random walk, and most analyses are based on this assumption. But many of the tracks you just saw also show a meandering pattern, where the ant turns left and right more or less regularly. By the way, I got these tracks by placing whole colonies of Temnothorax rugatulus ants in this arena. It is pretty huge compared to the size of the ants and completely empty. After about 5 hours of filming and automatically tracking the ant, I get a Jackson Pollock painting, or at least something close to it, and it's made up of huge big data. How to test for the non-randomness of the apparent meandering. Therefore, I first use a random walk null model, and then I measure the turn autocorrelations of the tracks. I create 2000 simulation tracks for each of the 1400 ants by shuffling around the order of turns in the tracks, which means I preserve the overall squiggliness of the track, but I remove any meandering that might be in the ant tracks. If that meandering isn't in the ant tracks, we should see similar numbers of turn autocorrelation. And that is a measure where 1 would be turning always into the same direction, -1 means perfect zigzagging or meandering, and 0 is no pattern. In this results plot, all 1400 tracks are lined up on the x-axis, and the lower the y value, the more the ants are meandering. And we see that 80% of the ants meander significantly, here shown all in the green dots. If we take a closer look at this remarkable track, it seems that the ant is meandering on multiple different spatial scales, just like a fractal. But it's challenging to show that this is truly a fractal, but still it's an interesting thought. And it still holds that there are multiple scales of meandering behavior in those tracks. Another interesting thing is that this ant crosses her own path not a single time. And in fact, 74% of ants cross their own paths less often than their random walk simulations. And this means that the ants don't waste much time searching the same area twice. And that is not a trivial task, since a perfectly systematic search pattern, like this meandering pattern here, in the real world, where there are obstacles in the way and navigational noise, there are a lot of crosses in the systematic pattern, even more so than in a purely random walk. But these ants could also achieve this little crossing by just going straighter, possibly leading them into enemy territory and requiring a long return journey. But most of the ants don't do that. They instead stay closer to the nest than their random walk tracks. So by combining the systematic meandering and random movements, ants walk more space-fillingly than a random walk, while also remaining less susceptible to the noise than a rigid geometric search pattern, making this probably a pretty efficient way to search for their resources. Thanks to my lab, including the undergrads that spent many hours correcting tracks, my collaborators, and funding sources who all made this work possible. The paper about this work is currently in review, and I will post a comment once it is published. Thank you.